Welcome back to Coding the Sounds of Music. In this video, we're going to learn how a microphone works. At this point, make sure your TI Innovator Hub is connected to your TI Inspire CX2 graphing calculator. Also, please navigate the TNS file to Microphone Activity Background. This is probably on page 1.27. Remember to use that control clickpad to move left and right. Pause your video now to do the navigation and then resume when you're there. On this page, Microphone Activity Background, you'll find a summary of the different ideas and concepts that I'll be discussing as we go through this video. Return at the end and read this as a review for the ideas and concepts that have been discussed. Before we get into exactly how a microphone works, let's go back and think through a little bit about the speaker. Remember from the previous video, we said a speaker is a device that takes electrical energy and converts it into mechanical energy. Remember, we talked about how electricity moves through a coil of wire, that's a loop of wire. It produces an electromagnet, and that electromagnet interacts with a permanent magnet in the housing of the speaker to push and pull on a big piece of cardboard that's in a cone shape. That's the part of the speaker that pushes and pulls the air. And that this is how sound is made with a speaker. And that the electricity that is fed into the speaker can have a pattern in a quality of the electricity called voltage that represents the sound. So for example, if a electrical signal with 440 hertz, that's how many times the electricity's voltage goes up and down, is fed into a speaker, it will make the speaker's cone vibrate with 440 hertz. And that 440 hertz of vibration in the speaker causes the air molecules in front of the speaker to vibrate at 440 hertz. And that wave can travel through the air, and when it hits your ear, the air in front of your eardrum vibrates back and forth with 440 hertz, and so does your eardrum, and you register the sound of tuning A in your brain. A microphone is exactly the opposite of a speaker. A microphone takes mechanical energy in the form of the energy in the air molecules moving and converts it into electrical energy. So a microphone can take the sound waves that come from a person's voice and change that sound into electricity that has a voltage. That's again a quality that talks about how much energy is in the electricity, and it makes that voltage go up and down, and the up and down patterns of that electricity mirror the vibrations of the air particles in the sound wave. And so a microphone is the opposite of a speaker. Let's navigate to the next page. Control, clickpad to the right. Here are instructions for the microphone activity. This simulation shows a 500 hertz air pressure wave hitting the diaphragm of a microphone. The diaphragm is a thin piece of plastic in a dome shape that is in the front of the microphone that is free to move back and forth. It's just like the cone of a speaker, but lighter and smaller. Notice that in this simulation, the voltage graph increases and decreases as the air pressure from the sound wave increases and decreases. I'm going to play the first part of the simulation, then we'll pause the simulation, and I want you to do it on your calculator and explore different frequencies. I'm going to go to the next page, press Control, click Pad to the right, and here's the simulation. I'm going to bring my TI Innovator Hub close to my, well, microphone so that you can hear the speaker play. I'm going to press Control R to run it. Notice in the simulation the blue sound waves on the right are pressing and pulling on the diaphragm of the microphone, and that diaphragm is attached to a permanent magnet that is on the inside of a coil of copper wire. As that magnet is pulled back and forth in the coil of wire, it pushes and pulls on the electrons. Those are little bitty particles inside the copper atoms. And as they're pushed and pulled, they gain and lose energy, which is what's measured in voltage. And so the graph on the left that you can see is a graph of the voltage. That's the energy of the electrons. So you can see that the mechanical energy of the blue sound wave on the right gets turned into electrical energy. That's the red voltage wave on the left. And I want you to change the frequencies and play with the simulation to better understand how a microphone works. To escape, I'm going to press the escape key on the calculator, and then I'm going to press the enter key one more time. That will return me to the shell. When you're finished, resume the video and we'll wrap this up. Well, I hope that simulation helped you to visualize how a microphone changes mechanical energy into electrical energy. That electrical energy, which sometimes is called a signal when it has sound information in it, is nothing more than a wave of voltages. Sometimes that signal is fed into a recording device. A recording device like, say, a tape recorder can record the patterns of that electrical signal for later playback on a speaker. Or perhaps it's a digital recording device which stores that electrical signal pattern as a representation of ones and zeros. And that's probably how you're hearing my voice, is ones and zeros are streaming across the internet. Or it's how you maybe listen to music on your personal music player. Sometimes that signal is fed into something called an amplifier. An amplifier is an electrical device that puts more energy into the wave. So the signal that comes out of the microphone doesn't have a lot of energy. But when you put it into an amplifier, it amplifies or makes it larger, and then that signal gets fed into a speaker, and the speaker can play very loudly. For example, this is how you would hear it in assembly at your school. There may be a person speaking through a microphone. That signal goes through the amplifier, and then it goes to a speaker so that you can hear what the person is saying very clearly. So we've talked quite a bit now about speakers, microphones, hearing, and sound waves. Our next activity is on the tempo of music. So stay tuned for our next video, and I'll see you there.